This is Victor Sanchez, fall semester. The course name is Engineering 120 DC Circuit Analysis, part of NMS University. We're going to be going over the breadboard and 5 different measurements on the breadboard. First we have to understand the breadboard. There are different rows and columns. First, we must understand what each row is. Each row is numbered 1 through 60. So we start from 1 all the way across to 60. Each row is determined by the letter from the number. Then each column is determined by the letter. So if I want to, like how I have this resistor on row 25, column H, and row 30, column H, and those are the resistors attached there. Something you must know about each column: within the number columns, in this general area, within the number columns and the letter rows, there are wires hidden under each row. So the whole row of 45 in columns, like in the whole row of 60 in columns J through F, the whole row of 60 has a hidden wire. You head off to the new letter section, and there's another hidden wire under those. And now for the positive and negatives, there's a hidden wire on the columns straight across. We're going to start off with our first measurement, which is going to include the resistor that I have already attached on row 25, column H, and row 30, column H. Now we're going to attach this to the same row 30 and the same row 25. Now that the rows are attached, we're going to attach this to... Now that it is attached to the multimeter and it is connected with the wires, we get a resistance of 5.01 kilo ohms. That is measuring the resistance of the resistor that is connected, which will get you a resistance of about 5.1. The next measurement that we're doing is going to be connected to row 60, column J, and row 60, column F. Now we attach it to the multimeter to the respective wires. Now that they're connected, we get a reading of 0.1 ohms. Due to the margin of error, this should be about a flat 0 ohms. The reason is because of the hidden wire beneath. Ideal wire has 0 ohms, so it is just connecting a wire to a wire, so the measurement will be 0 ohms all the way across because it is connected to the same wire. The next measurement we are doing is row 55, column negative, and the positive on the top. Now that they are connected, we connect it to the multimeter. Now the result we get is overload mega ohms. The reason why we get an overload of mega ohms is because the wires are disconnected and have a resistance that is way too high for it to measure, and as a result we get an overload of mega ohms. The next measurement we are doing is row 50, column F for the red wire, and row 50 for column E for the black wire. Now that it is connected to the multimeter, we get a measurement of overload mega ohms. Same reason as the last, because these hidden wires are not connected, they are disconnected, and as a result it is an overload because there is too high of a resistance. The next measurement is row 5, column negative on the bottom, and row 10, column negative on the bottom. And we get a reading resistance of 0.1 ohms. Again, the reason is because the ideal wire has a total of 0 ohms.